guess we can start. Let's see. Can you hear me? Ha. Is it? Can you hear me? Okay. So I guess we can get started. So I guess we have finished the old topic already, right? So we are with the new one. Okay. So I guess that marks the end of the first half of our course. The first half of course is the main idea, probably except the first topic, we talk about data, right? How to summarize data, talk about mean, variance, and how to give a first run analysis, right? Looking at the mean, variance, kurtosis, skewness, correlation coefficient. And after that, we do a detour and talk about probability, right? Probability is a measure of uncertainty, right? That is already by itself is already very useful, right? And then we talk about random variable, and that can be applied into many contexts when you try to understand the future uncertainty where you make a business decision, right? You try to model how many consumers like your product, how many consumer will arrive in the next 10 minutes, so on and so forth, right? And we didn't talk about data too much, except that we use the data to estimate our model, right? Because that is how we say, okay, looking at exponential distribution, right? We look at how can we estimate lambda, or the Poisson, how to get the lambda is looking at the mean, right? That is, we don't talk about that, but it's what is called matching method of moment. Try to equate the sample mean to the population mean. And from this class onward, we will be, let me close the door. From this class onward, we will basically working on data, okay? From now on, everything is related to data, and everything is directly applicable. I mean, of course, when we set probability and random variable is very directable, right? So everything we learn in this class is has direct application, okay? And today in particular, we focus on looking at sampling, okay? It's data collection. Okay, but let me go straightforward. I'm not going to review what we have done last week, but I hope that we cover so many stuff, it's clear, no need to. An exercise can help you to make you do some revision. So the idea of sampling, actually, you go back to the idea we have to distinguish what we mean by population and sample. Okay, you can imagine population is the big picture we want to study. It's the thing that you want to understand. For example, if you want to understand, okay, how much a university graduate would like to spend on their iPad, or spend on the laptop, right? Or spend on the clothing, so on and so forth, right? And that's a subject we want to study. Why? Because basically maybe we're doing marketing research, doing how to target this type of customer, right? And this is our population. But unless you're very rich, you're unable to study every single university student in Hong Kong. I mean, even in Hong Kong, right, you can't even go to everyone. So what you're going to do is you would do a subset, right? It's a much smaller part of the population, okay? And by doing so, you try to say, get the knowledge, the pattern you learn from the smaller subset, okay, small group of that. You try to see, you try to infer, to extend the knowledge from that, okay? The idea is like this. Graphical is like this, right? Say, suppose this is the thing you want to study, right? Usually called population, right? And you can never able to meet every single individual here, right? Either it's too expensive, either the time constraint, right? It takes, suppose you want to ask, right, how much do they want to pay for your product now? It would take forever, I mean, or at least a very long time to ask everyone, right? So all you do is instead of asking everyone, you get some people here. That's called sample. Okay? And practically speaking, we always study sample instead of population, right? Except the government, which have all the information of everyone. Otherwise, we can only have sample. And for business application, sample is very common, right? Because you are able to only collect the data. Or you can think about predicting or working about time series problem, like finance, right? And then you're going to predict the price in the future, right? And you look at the things in the past, right? But the past is just a realization of a particular scenario, right? You can imagine the world consists of multiple universe, right? What you observe is just one possible universe, right? So you don't really actually know everything, right? So you have to rely on the universe you observe, okay? And we try to make prediction, right? And that's the idea. Or as many of you are studying accounting or auditing, right? And that's what you do, right? You base on, you don't look at count every single inventory for a firm, right? Instead, you go to randomly choose a warehouse and try to see if that warehouse actually align with the statement from your client, right? So that is the way to do it. You were never able to observe things, but you try to guess from some evidence, right? And that is how we do things, right? It's very difficult to observe everything, right? But just like, I don't know, some of you may be in relationship with a boyfriend or girlfriend, right? You cannot perfectly monitor what he or she doing, right? Even you look at his or her phone all the time, but he or she may not have the phone all the time, right? So you try to observe some of the signal, right? Whether he or she give you a flowers or gifts or whatever expensive thing, right? Whether talk to you, whatever, there's some signal, right? And try to from that specially selected occasion, you try to see whether it's good or not, right? So that is the idea, right? Try to guess what is going on based on limited information, okay? So the information we collect is a sample, and we try to use that to make a guess, okay? So the goal have to generalize some from the small picture to the big picture. One of the very important thing is this have to be representative, right? If you try to, the small picture is not representative enough, then it's not good, right? Because you have to be, the small thing you pick cannot be very particular. They have to be general. So just some technical thing here is how usually you define population. Usually technically, population you can think about as a histogram or chart when you learn in the before, and then usually you would summarize as a frequency table, F, and then usually what we're interested in population is mean and variance. Okay, how much on average people want to pay for your product, and on what is the variation with the variance of that. And sample is what we call an observation, right, from population. And what we said, what is representative, is that you consider that as one way to do it is a random sample. You can imagine you close your eye and draw one guy, one object, or one subject from the pool, right? Suppose I want to know how much a CUHK undergraduate student would like to spend on their lunch, okay? And to do so, I should close my eye, just grab one people from the canteen, okay? That is one way to do it, okay? And as long as I do it randomly, the key thing here, the random, is the probability function, okay, or the PF or F is exactly same as the population distribution, okay? So let me repeat, this is very important, although probably you implicitly know is when you call random sample, okay? The sample is a random variable, right? Because depending on which people you draw, okay? And the probability, okay, that the value equal to that particular value, okay, if you do a random sample, should be same as the frequency and the population. Put it this way, very simple. Suppose in CHK, I think that's true, 60% are female and 40% are male. Okay, that is a distribution. There's no probability. Okay, and suppose I do a random sample, I particularly pick one guy or one person, okay, and that means that there will be 60% that is female, 40% from probably 0.4 that will be male. Okay, so that's random sample mean. The distribution, the frequency table, the bar chart, okay, which you don't observe, but hypothetically that's there, right? And that will equate to your probability, okay? So that is how the probability take into place, because the population, there's no probability, right? Because there's only how many people, how many female and male in each case is fixed. There's no probability. That's a number. We just don't know yet. But anyway, the way that we pick, if you random draw a sample, okay, randomly pick up a person in a railway station or on the school bus, you should expect, if you do it properly, 60% of them would be female, 40% that would be male, okay? If you do just one, okay? But you can imagine that if you do many of them, right? 60% actually will be female and 40% will be male, okay? And usually when we write sample, we will write x1 up to xn. And do note that the x is capital letter. The capital letter in our notes or in other text is usually referred to random variable, right? When you have small letter font size, that usually is a good data. So that's why I try to be very careful here, okay? Is that clear? So we focus on what we call the simple random sample. Essentially means that there are many elements, I mean, potentially in the population. And if every element have equally likely being selected, okay, and how you select is independent, is simple random sample, okay? So if I go to the CC canteen, okay, Zhongji canteen to pick sample, okay, then it's not simple random sample. The reason being that it's not independent. Why? Because you are more likely to get people that is studying Chongqing College, or you are going to pick up people that like Chongqing Canteen more, okay? So usually if you've done correctly, you should be doing, I pick up some person in this canteen and the other person in another canteen, so on and so forth. Make sure that it's randomized, okay? And if I only do this in the morning, okay, also is a problem, right? Because I would not get people in the afternoon, okay? I have to do this every day, every hour to make sure that things are there, right? And I cannot just do it in the campus, right? Because some people may just stay at home, never go to school, right? I have to visit them, right? To make sure that it works. Or people just stay in the hostel, playing computer games, not coming out to the class. Then I have to go there, right? Or some people always stay in the library, don't come out. Okay, you have to visit them. Okay, so this is not simple. Okay, to get simple sample is very difficult. Okay, but we will sidetrack the issue of getting a sample. Okay, because how to get the right sample is already a class. Okay, can be a course already. So I will just assume we are able to do it. Okay, but in principle or in practice, that's not easy. There are many ways to make sure that this is done you have to do it correctly, right? Usually pay, or for example, you would do some adjustment, right? Because say, suppose you want to look at how people like the CHK canteen food, right? And you know Chongqing canteen is much bigger than other, then you should do more sample here. So it's a kind of waiting. There's some way to do it, but it's not the concern for us. But just assume we're able to have simple random sample, okay? And technically, simple random sample refer to, because we do it correctly, so each random variable is independent, okay? And they follow the same distribution as the population. So everything we do is good, okay? So that is the main definition. If you read simple random sample, it means that every single observation has the same mean, okay? Same variance and no covariance. What does that mean? Go back to the example of CHK female and male idea. It means that if I have n observation and if they are simple random sample, it means that everyone I observe, the n people I observe, each one will have 60% likely to be female, 40% will be male, okay? And the variance the same, okay? No matter which one observed. And the covariance with 0 essentially means that even if I have, say, suppose I observe 10 person, okay? Even though the first 9 person are male, okay? You still would believe the next one, 60% is female, 40% is male. Because each observation is independent. Regardless of what you observe in the first 9, the last one's still the same, okay? So that is the idea. Is that clear? So is the idea that everything would follow exactly the same mean, same variance, and they have still covariance and independent, okay? So there's a many strong property here. Okay, I'm not going to talk about those. So now we define, quite ironically, statistics. Okay, you learn statistics, right? But statistics here has 2 meanings. Statistics is the subject that you learn. Statistics, its meaning is a function of the sample. Okay, what does that mean? The sample you have is like a random variable. Say it's observation, whether say I talk to 10 person, I ask, what's the gender, male or female, right? So for 10 person, I have 10 observation, okay? And a statistics is trying to say how I'm going to summarize the information I got, okay, which is a random variable, okay? Example of this is mean, right? Mean is I look at average, on average, or median, or mole, maybe that's mole, right? Mole, maybe that's, in this case, mole is easier because female and male, right? Where man or more or woman more, right? Or if I ask 10 person how much they spend on their lunch, okay? And each person will give me a number, right? And average of those number is a statistics, okay? Do note that statistics is a function, okay? It's not a number, okay? It's the way that you convert your observation to a number, okay? And because of what you observe is not determined until you do it, which is a random variable, because before you do it, it's a random variable, right? After you do it, you're done, but before you do it, you don't know it's a random variable. So statistic is also a random variable, okay? And that connect to what we see in the first topic, sample mean and sample variance is a statistics, okay? And they're a random variable, okay? Because it depends on what data you observe, okay? So that is very interesting, right? We talk about statistics for half a semester. Now we define what statistics is. Okay. So in this class, we only focus on 2, okay, which is sample mean and sample variance, and that's it, okay? And of course, you can imagine sample kurtosis, sample skewness are the something you care as well, but in our class, we only focus on sample variance and sample mean, okay? And the reason why we focus on these two is because in our introductory class, that's the thing we care, okay? And sample mean, you can imagine that would be something very trivial, okay? It's adding all the observation over n, okay? Just to remind you that this is very different from the topic one we have. Topic one we have observation with data already, and we just add them, okay? Given the data add them, there's no probability, there's no uncertainty, there's no random variable here, there, okay? Here, they are random sample. So all of these are random variable, okay? So that's why the X bar, we have a capital letter, is a random variable. It's not a number, okay? It depends on what you observe, okay? What you observe, X1, what you observe, Xn, we don't observe yet, okay? It's a rule, okay? This simple mean, right, depends on what actually you observe, okay? For example, let me do this, okay? Let me make this exercise, okay? Make it easy. Okay, in the population, okay? Okay. You have a guy, okay? And he has $1, okay? And a boy more richer, okay? And this guy super rich, okay? And then I have another girl, okay? Who has a handbag, okay? Not very expensive, okay? And who has a very expensive handbag, okay? And another who has a super expensive handbag, okay? So the data, right? And look at this, the average, the population average is $2, right? Everyone $2, okay? And now, suppose I collect the sample of 2, okay? 6 people, 2 is good, okay? I collect 2 people. Then what would be the sample mean? It depends on who I got, right? Suppose I only got guy number 1 and girl number 1, then the sample average is just 1, right? If I get guy number 3 and girl number 1, I will have 2, right? And if I have, say, guy number 2 and girl number 1, I have 1.5, right? It really depends on who actually got. Is that clear? Okay, it really depends on what actually you got. So it's a random, because which one you got is a random sample, okay? So that is the idea of why we say the sample mean, right, is depends on the sample you got. So that's why it's a random variable, okay? So it have to be logically it's a little bit jump, okay, because it's much more abstract. It's not a number you average out. Rather, it really depends on what really actually you get, okay? So that's why we need probability, right? Because of why we want to study probability, because we need to have the idea of uncertainty, right? Because we don't know which one we got, okay? The probability is measure uncertainty is to allow us to handle this problem, because we are never able to observe everything in the population. We have to study the sample, and the sample is a result of getting something that requires to understand how uncertainty realized, right? Because this is only one scenario we got, right? But is that clear? Because what we observe is a random variable. That's the main idea why we need to study probability. Okay, so we spend a lot of time on learning those, but I hope it pay off. Okay? So as I said, we will focus on sample mean and in somewhat extent sample variance. Okay, sample mean is the major thing that we study throughout the rest of semester. We'll study sample variance a little bit, but the main thing is sample mean. Reason, because sample mean is already complicated for our purpose. Okay, and most of the time we care about the mean more than others. Okay, and we ask what about median, mode? Yeah, you can do that, but it's not usually you don't study those in undergraduate. Even in my graduate study, I will study little for those. We study variance. Do we study interquartile range? Not really. Only very rarely. So not because of that, because it's most of the knowledge we know is about mean, and most of the time we care about mean anyway. Okay, because mean is the way to summarize the data, right? So knowing the mean is already the best thing we want to know. Okay, of course, variance with how accurate is this one is also we want to know as well. But mean is the main thing we care. Okay, and now because sample mean that random variable is so important, in this class we basically want to study, okay, how would they look like based on the probability knowledge we have. Okay, and we will use the sample mean to guess the population mean. That is our goal. Okay, because we want to guess as a right, we want to study what is the population mean is our main major goal. And we will talk about, because the random is a random variable. Okay, we want to look at its mean, right? Expectation. Look at the variance, what it should be, and we look at how the distribution F or P, depends on what you like, looks like, right? Because that is what we learn in random variable class, right? We learn a distribution, we learn the probability function at P, right? Or the big F, right? And then want to know the mean and variance, right? So the same idea, because we care about the sample mean, okay? Then we want to look at this, okay? And we will learn the two very important result in statistics, which we call law of large number, okay? Which essentially said the following: the sample mean, X bar, if we have very large sample, X bar will be as close as to mu as possible. Okay, we'll define the formula, but they're saying that X bar will be close to the mean, mu, we want to measure if we have large sample. The idea is very simple. Just imagine I want to know the gender composition in CHK. Okay, how am I going to do it? I try to meet person. Okay, meet the first person, turn out to be a female, I record it down. Second person, I record it down, and keep looking. If I look enough, okay, what I have, the data sample mean will be approaching to the population one. So that's the idea. Is that clear? The second one is called central limit theorem. Okay, and actually that related to bell curve, and that's the reason why the bell curve is so convenient. The idea is law of large number, which we'll talk more detail later, is the sample mean, right, will be close to the right. So here, right, what it means, the law of large number means, suppose I have a sample of 2, right? As I said, right, I pick up 2% from this one, right? And what I said is, if I keep drawing many times, okay, every time I pick up 2%, okay, and I close my eye, draw a person. If I draw this enough, right, then it should be fine, right? So instead of drawing 2%, I draw 3, 4, or 5, or 6, or 7, or 10, up to 1,000, 1 billion, right? Actually, you can imagine that each one would be equally likely to pick. And actually, what you observe, the sample mean will be same as the population one, right? So let me repeat the statement. Law of large number is, what I do is close my eye, okay? I close my eye. I pick, I use a black, okay? I close my eye. I pick one guy. I close my eye, I pick another one, and so on and so forth, okay? I close my eye. I do keep doing it. It may be the same guy, maybe different guy, but if I do this enough, okay? And I calculated my sample mean, will be same as population mean, okay? That is a law of large number. And central limit theorem is talking about the distribution, okay? Because I only care about the sample mean, right? But what happened to the distribution of the sample mean, okay? Because it's a random variable, right? And what it said is when the sample size is large enough, it will be following a bell curve, okay? And that underlines what we do for the rest of the semester. But I will be making more formal later. I just give you an idea what's going on, okay? Today I don't know with time, but if we do, we'll talk about the T distribution, which later you will see why we do that, okay? But I'm not going to, I'll talk about that when we do, but let's skip this part. And the last one is called binary data. And actually we talked about this already. We look at how many students are male and female, right? The data is either 0 or 1, okay? And compared to the example, we said how much students spend for the lunch, right? It's a number, right? But here focus 0, 1. The binary data turn out to be things getting easy because binomial or binomial trial is at work. So we don't really rely on central limit theorem. Okay? So everything actually we know exactly is going on, and things become easier when we talk about binary. Okay? But it's special case. So everything will be even easier. So that's why we'll do it later. Okay. So now let's go to talk about this. Okay. We don't prove it. Okay. But what here is said is a little bit tricky. Okay. What it's saying is the expectation of the sample mean is the true mean. Okay. What does it say? It said the following. Remember, sample mean is a random variable. Okay. And potentially, you can get many samples. Okay. And average of those samples is same as the original mean. Okay. Let's do it graphically because it's a little bit convoluted idea. Look at the picture. Okay. What I said is consider the case you only do 2 samples. Okay. And potentially you can get the green one, right? $1 guy and $1 girl. $1 boy and girl, the average is 1, right? And potentially you can also got the orange one, right? Rich boy and poor girl, right? The average is 2. Okay, I have the first time I get 1, the second I get 2. But I can also have the purple case where I have $2 boy and $1 girl, right? And that case, the mean is 1.5, right? And potentially I can do many of those. Okay, and average of those will be exactly same as the overall population mean mu, which is $2. Is that clear? Let me repeat because this is very convoluted to understand. Okay. Now, look at this. In this population, we have 6 people, out of which 3 are boy, 3 are girl, different wealth. Okay. And you want to ask how much they spend on their lunch. Okay, say. Okay. And we only do 2 samples each time. Okay. If we do 6, then we're done, right? Because there's no way you can do it. Only do 6. Okay. We can only do 2. And do note that we only just do 1 of them, but right in the real world, but suppose hypothetically we do many of these. Okay. We close the eye, pick up 2 person. Okay. Maybe we pick up $1 boy and $1 girl. Okay. The average money they spend on the lunch is $1. Okay. And maybe we end up with $3 boy and $1 girl, and we have $2. Right? And maybe we end up with $2 boy and $1 girl, we have $150. right? And potentially you can repeat this process many times, depending on who you pick, that many number, right? And we're asking average of this number will be the overall mean, which is 2. Okay, is that clear? So it's the on average, okay, if you do this enough, the sample mean is exactly the population mean. Okay, and this is a very nice property we will call unbiasedness. Okay, that means that if, although we never do, but if we ever repeat this process again, and again, and again, and if each time I observe the sample mean, okay, there will be many sample mean. Average of those sample mean will be equal to the population mean. Okay, but do note that we only do just once. We just hypothetically suppose we do this many times, that we can get what we want. Okay, but we don't do many times. But at least in principle, if you're to repeat that, okay, that is what we want, is called unbiasedness, and that's a nice property. Okay, and that is the idea why we can do science or experiment, right? Because some people do this sample, you get data. You do this sample, you get data. I do this sample to get data, and average of those actually will get what we want. Okay, that's not a problem. Okay, so that is the idea. Okay, so that's why property is very difficult to understand, but I try to convey the message out. It's not easy to see, but I hope I write down already, right? You sample many times, and we have many sample mean, and average of these will actually the population mean. Okay, and in the next topic, you will see why the sample variance we have is n-1. Okay, because if you do n, that is not what we want. Okay, we'll talk about this in the next topic, probably next week or the week after. Okay, so that like this, right? Population, you can collect m samples. Okay, and each sample you have sample mean. Average of this sample mean is this called the expected one. Okay, let me give you the more numerical version. I hope that would be convince you this is right. Okay, consider following case. I have a data which is very simple, 1, 2, 3. Okay, that's 3 observation, and I do very simple idea. Okay, 3 numbers, the population mean mu is just add them up divided by 3, right? That's what you learn in topic 1, right? There's no uncertainty here, right? 3 person, 3 of them, each one have the wealth 1, 2, 3. Okay, mu is just simply you learn from topic 1. There's no probability, there's no sampling. Okay, now consider the case I close my eye and pick up 1 person. Okay, and I do simple random sample. By simple random sample means 3 individuals, each one will be equally likely to be picked up, right? So which that is why said, right? Because I only have 1 person to pick up each time. What I see that guy or the person, the observation is the sample mean, right? If only 1 person, right? I observe this guy's 2, the sample mean is 2, right? So that's why each one equally to pick. The sample mean will be just 1, 2, 3. Each will be equally likely. Okay, and you can calculate the expectation of this sample mean, right? Which 1/3 of 1, 1/3 of 2, 1/3 of 3. So average is exactly 2. So this sample mean we denote as expectation, or mu of x bar instead of mu will be just 2. Okay. Now, to see, you understand, I give you a little bit more challenge like this. Okay, then we have break. Consider case we have 2 sample. Okay. Again, we have 1, 2, 3. Okay. And really depends on who you pick, right? Because you close your eye, pick again, right? And this first entry, okay, is the case where you pick 1 and 1 again. Okay, the first time you pick the one guy, and the second guy pick one guy, and average of 1 and 1 is 1, right? And for here, y 1.5 is you will pick the first guy is 2, the second guy is 1. 2 and 1, average 1/2. Okay. And the next one, y2 here, the first guy you pick is 3, the second guy picks 1. So 3, 1, add together, divided by 2 is 2, right? You can do the same for the rest. I think it's okay. Is it okay for the rest? I think it's okay to see why we have 9 entry here. 9 scenario, dependent on whom you actually got. Is that clear? Right? Because it's a simple random sample because everyone is equally likely to be picked. Okay? And that means this 9 scenario is equally likely. Right? So each 9 scenario is uniform distribution with each outcome is 1/9. Right? And how many 1 you have? You only have one scenario of 1 is 1/9. Okay? How many 1.5 you have? Right? You have 2 1.5 have. So that's why 2/9. Right? And how many 2 have? You have 3 2. So it's 3/9. Okay? And how many 2.5 you have? You have 2 scenario. Right? And finally, how many 3 have? You have 1. Okay? So that is how you would get this one. Is that clear? Right? Is that clear how you get this one? Because 9 scenario, each scenario is equally likely because simple random sample. Okay? And you want to calculate the average of this sample mean, right? Average, we just this multiply this plus this multiply this plus this. And this you get 2. Okay? Not surprising because you can prove the theorem, but we don't prove it. But what it essentially showing you that, okay, if I do this sampling many times, although you don't do it, but hypothetically, okay, this is what we get. Okay, so this gives you some confidence or some hope that we do sample mean is likely to, if we repeat enough, we get what we want. Okay, so that's the first thing. Okay, so and we will talk about continue after the break. Okay, so it's not too much thing. I mean, I guess there's a more terminology rather than a lot of difficulties in the math, but you can see from the rest of the course, it's like we'll introduce some concept and knowledge and show you how to do it. It's more like we don't derive the solution. More. I mean, we try to give you some idea, but the main thing is more procedural. It's algorithm. You can imagine it's like accounting, right? You give an accounting rule, or you apply the rule, and this is how it works, right? This is debit, this is a credit. It's a more or less a more like accounting rather than math class from now on, because it's like this is a procedure, you do this and that because it's a standard procedure to do the things. But of course, we try to give you why they are good. But you will see it's more procedural stuff. Okay. But if you're a QFN student, probably you need to know the mechanics, which is hiding under the technical slide. So you have to read those. But other than that, let's have a break of 15 minutes, and then I open the new reply so that you can tell me I'm going too fast or too slow. It's a break of 15 minutes. So let's resume at 10:35.
And you can ask me or leave it and you reply, because in this way I know how fast or how slow. I guess we should resume. Okay. So let's see how well we are, where we are. Happy EP. What is happy EP? I don't know. Happy weekend. Okay. Probability. Yeah, that's exactly true. So I guess the idea is exactly what we mean by continuous distribution, right? Because a rainbow game, right? And the probability hitting this point is essentially zero because the probability of the whole space is much bigger than the point, right? So that is exactly why continuous distribution you cannot define for each probability for each point, right? Because exactly one point will be zero. So but we didn't talk about the geometric way to define probability. But that is you can do the same. Very good. Every single understand, but when they put together, I don't understand none. I mean, you have to be more specific how I can help you. But I do recommend our TA to you if you have problem understand, because I think he is super good, super nice. So you can see how he grade your assignment. Okay, very carefully done. So I hope I try to help, but if you don't tell me, I really can't help you. Okay. Yeah, today everyone know it's Friday. That's good. No one make a mistake. Okay, windy, cloudy, sunny. Okay, that's good. Yep. Average sample mean is the expectation population mean. Yeah. Yeah. Actually, don't need to say expectation population because population mean is by itself is already a number already. So you don't have to use expectation. Okay. Because already just a number, right? Normal distribution. Yeah. Yeah, that is exactly what we just said. Yeah, that's correct. Is the mean of sample mean is population mean. Okay. Mean of sample means is population. It's not itself not the same. If the same, then we're done. Okay, but it's not. I mean, it's average of those sample mean. So very good. Today we don't have 1 and 2. Very nice. And okay, still some of you think can't follow. I try my best to see if I can make it easier, but not that easy. Do you know that when a short guy is waving at you? Oh, this one is good. I like it. But why is a guy, but not a girl? But anyway, but it's a good one. I really like it. So 鋼琴家最怕邊隻染髮劑？染髮彩冇得彈。Oh, that's good. This is a good one. This is a good one. When will I end the lesson? Yeah, same as 11:40, 11:15. This one is oh, this is a good one. This is a good joke. I like it. Yeah, but this is a very nice, it's a nice one. And also microwave is very good. Yeah, it's good to share happiness. So the joke is good. Yeah, I like this class because many of you like to share jokes with people, with us, so I really like it. So I'm not going to go to this detail, but you can see I can do 3 samples, and you will have end up like this, and then I also 2. Okay, and you can prove in general this is true, but I'm not going to do anything on this. Okay, instead I will talk about this one. Okay, and this one is the sample variance. Okay, it's talking about how, because each sample you have is different number, right? And how different the number, okay, will be given by a very simple formula, okay, which I don't think we'll prove. It just depends on how large the sample size is. The larger the sample size, the smaller the variation you got. Okay, and it depends also proportional to the original variation. Okay, so sigma square is the original one, the population, how spread they are, right? And n is this one, and you take a square root will be the sigma x bar. Okay, and to prove it is not difficult. Just rely on the math we have. We just variance of the sum is sum of the variance, and variance of n is that is the main proof. Okay, but I'm not going to prove it because of the time or with the math. I will just, instead of proof, I'll give you an example to convince you this is true. Okay, the proof is actually very simple, but I'm guessing if I give the proof, most people would be sleeping. Okay, I mean the proof is actually terribly simple, but I just not do the proof. Okay, so example to show this is true. Remember, I have an example with 3 numbers, 1, 2, and 3. The sample average is 2. Okay, so population average is 2, and the population variance is what? Population variance is, you take, remember this is data, right? So you take each number, subtract from its mean, take a square, and do the same for every number 2 and 3, and divide by 3. Okay, this is population, so you only divide by 3, not 2. Okay, because n is 3. Okay, 3 numbers, the variance. So this variance is 2/3. Is that okay? So this is what you learned from topic 1. So that should be nothing new there. So what's new here is, suppose I have a sample size of 1. Okay, I just close my eye and pick a number. Okay, so it's uniformly distributed with 3 numbers, 1, 2, 3. Each is equally likely to happen, and because I just do one outcome, okay, and each one realized with probably 1/3. Okay, as the sample mean, because I only do once, right? Whatever number I pick itself is sample mean. Okay, And we have already shown the average is just 2, which is same as the mu, right? So how to calculate variance for x bar, right? Would be x bar, right? 1 minus 2 square is 1, right? 2 minus 2 square, 0. 1 will be 3 minus 2 is 1, right? So how you get this guy? This is 3 minus 2 square, right? Now, the variance will be just this multiply this, this multiply this, this multiply this, right? 2/3. Okay, so you can see if I just do one sample size, the sample variance or the sample mean is just same as the population mean, right? Why is true? Just from the formula. Go back to the formula. X bar for n equal to 1, sigma square is equal to sigma square x bar, right? When n is 1, the same. Okay. Now I show you the next one, n is 2. Okay. N is 2. I also got the formula here. Okay. Remember, no matter which the sample size, right? Sample size 2, n is 2, right? This is still true, if you still recall. All right, this is something from the average of sample mean is the population mean, right? Because mu is 2, right? We learned that from the other slide. So remember how we get this 6 outcome, right? Is from a table, right? We have 9 outcome here, right? Maybe I should put 9 over 3 here to make it easier to see, right? 9 over 3, okay? And in each case, right, we can take this number. How we get this is 1 minus 2 square, right? And how we get this number, right, is 1.5 minus 2 square, right? So this basically for each number, you take the square distance from mean, right? That's what the variance means, right? The square distance from mean. And you look at the variance will be the average or weighted square difference from mean, right? Just 1 multiply this plus, right? So on and so forth, right? That's how you get. And turn out to be 2 or 3 over 2. Why 2? It is the n, right? You do 2 sample, the variance will be half of the original one. Okay? If you do 3 sample, the variance will be 1/3 of the original one. Is that clear? Is that clear what it shows? Although we didn't prove it, but this is what it is. Okay? So here's just showing the example that depend on the sample size, the n, the bigger this will become smaller and smaller. Is that clear? Okay. So this 3 you can go to check if you want, but what I want to show is the idea that when n get bigger, right? It's a fraction, right? And what you imagine, the numerator keeps the same, right? When n increase, right? But this guy goes up, right? Goes up. Okay. From elementary school, for your denominator goes up, the number itself goes down, right? When n get bigger and bigger, bigger, the variance become 0, right? Is that clear? Okay. So, and on average, right, the guy is concentrated here and the variance is very little. Okay. let me repeat the statement. Regardless of n, right? The average of the sample mean is population mean, right? And the variance is very small, right? It's shrinking, right? And that means what? That means that is the following important result we call law of large number. Okay, essentially means very complicated. It means the probability that they are different, okay, is less than any number you mentioned is 1. Okay, I should make it less technical. Okay, it just simply means the following. Okay, suppose the mu is here, a number line. Okay, mu is here. Okay, and what it said is, on average, this is here, right? So suppose you may have a one observation here, and the observation here, right? And average is mu, right? And what it said is, okay, when n get bigger and bigger, okay, these things are actually getting smaller and smaller. So maybe let's make this one. Okay, let me do this. Okay, let me do multiple. Let me double line that I hope that would be more figurative. Okay, and let's do this. Okay, it's all the mu. Okay, and suppose you do n equal to 2. Okay, and what might observe is the data looks like, you look at, remember, it's like that, right? 1, 2, 3, right? 1, 2, 3, right? It's 1/3 of them, right? And if you do, sorry, n equal to 1, okay, and n equal to 2, what you have is like this. One, 1.5, 2, 2.5, and 3, right? And this is 1/3, right? And this is 2, 9, and this 1, 9, I guess. Yes, okay. And it simply means n equal to whatever very big number. It will be something like that. Actually, you can see. Something like this happening. Okay. And the more and more you have, it will be very central in this one, because the variance is very small. That means that this outside is very small, right? Because the variance is very small, right? And what it said is, when you get a very large sample, this thing basically become very small, only concentrated in the middle, such that the variance becomes 0, right? When variance becomes 0 means everything is concentrated at the center, right? Because variance becomes 0, right? Getting smaller and smaller. So when actually at the end, when n go to infinity, right? Large. When n go to infinity, there's nothing left. There's only one bar here. Everything becomes 0. Maybe I use. So only this. Look like that. Everything is 0 except a one central bar here. Okay. So this is the idea of what we call the law of large number, right? When n is super big, the average is almost 0. You can imagine almost like a bar. Okay. But of course, we will talk about this more carefully. Okay, but that is what that statement means, maybe I should I will change a little bit. This is a little bit more technical, but that's what it means. It means the probability that for every number, the difference between the bar and the mu, okay, less than some number you mentioned, okay, is going to be 1. Okay, it's always within epsilon distance, right? So I mean, in this one, it means the following. If you want to say the statement actually means this mu here, okay, it means that x bar maybe here, okay, whatever. But what it said is, whatever you give me epsilon, whatever number told me, okay, the probability that you give me n epsilon, okay, I would say mu plus minus epsilon, right? This is mu plus epsilon. This is mu minus epsilon. It means that x bar is always within this range. Okay, that's the formal statement means. Okay, when you give me the epsilon, okay, I can give you an n big enough such that x bar is for sure within this range. That is called the statement of law of large number. It's very technical, but it simply means that when n get bigger and bigger, the x bar will be as close to mu as possible as you want. The larger the sample size you give me, the closer. Okay. Let me repeat again the statement because it's a little bit more tricky, because I think it will be good to have an idea. Let me draw it again. So let me say it again, the statement, okay? It said the following, okay? Mu is here, okay? Which we don't know the number, but what it said is, give me any positive number epsilon bigger than 0, okay? I can draw a epsilon, mu minus epsilon, and mu plus epsilon, okay? That's a range, okay? The random variable, what we have is, we don't know the number, which x bar. What the statement said is, x bar, of course, depends on n, right? And the probability that this sample mean fall within this range, okay, will be probability with 1 if n is very large. Okay, that is what it said. It's always fall within this range. Okay, for every epsilon you want to give me, I can give you a big enough n such that they fit in. That is the limit idea. But for our non-technical audience, that's very simple. Just say, if you give me a big enough n, mu will be as close as x bar as you want. Okay, if you give me bigger n, they will be very close, as close as you want. The bigger n we have, the smaller this boundary we have. Is that clear? That is the idea. Okay, and if you go to infinity, this bump, right, it's always inside this range. Okay, because why so much difficult? Because it's probability in a range, so we have to be very careful how we define it, right? Because it's continuous random variable, right? You can't define a probability equal to that. That's not possible, right? Have to be very careful to define the range, right? I cannot say the probability x bar equal to mu, that will be 0 event, right? Because if continuous random variable, we have to be careful to say within this very small interval, there's always 1. Okay, no matter how small you can mention. Okay, so I know it's kind of tricky, but probability is like, if you want to define precisely, this is what it means. But for our imprecise idea, just say the sample mean, if large enough, if you get a very large sample, you get to very close to the population mean, right? There's no uncertainty here, right? Because we mentioned the unbiasedness is, we do many sample, average of those is the sample mean. But what it said is, if you do big enough sample, no matter what you do, is exactly sample mean, right? So let me repeat the statement. This, what we call the law of large number, essentially is the following. If we do a large enough sample, what you will get is exactly this population mean. The sample mean will be the population mean. Is that clear? So it's very powerful, right? Because we don't rely on probability, right? As long as you do big enough sample, there's no uncertainty there. Exactly what you want, what you get is what we want. Is that clear? Okay. Unbiased have to say I have to do many sample, but in the real world just do one, right? But here say if the sample size is big enough, right? So just the idea is, suppose I in CHK, right? I stay in the subway station for 1 million years. Okay, I exactly got how many boys and girls in CHK, right? Exactly, that's the uncertainty. Okay, it's different from saying I keep doing many different samples. Okay, is that okay? So don't worry if you don't get it. Oh, sorry. They're only for conceptual purpose. I mean, I'm not going to ask you how to define that, how to do that, but they underlie our analysis. Okay, it's not something is directly I would ask you what it is, but they are the reason why how we do our job after this. Okay, it's okay you not understand this because I don't think I fully understand what's going on until I do a master PhD. So it's okay you not understand, but I hope I convey the message to you that if you do a very big sample, what you get, the sample mean, is exactly the population mean. Okay, there there's some difference, but the difference is so minor that you can ignore. Okay, if you do a large sample big enough. Okay, and the second way, there's a proof behind, but I'm not going to prove it. Okay, now the next theorem that is super important as well is closer to what I said. Right, what I said is if I have large enough sample, right, and the sample mean will be exactly the population mean, right? Might be some difference, right? Will be some maybe very close to that, right? As close as you want. But remember, there's still maybe some deviation, okay? And how the deviation looks like, okay, is what we call central limit theorem. Means it will look like a bell, okay? And basically, you have already seen that. I have hinted in the diagram here. Look at this one. Starting a flat, and you start to have a look like a bell, okay? And you getting look like a bell, and eventually become a line. So what it essentially said is the following. Central limit means the following. Okay. Maybe I just draw. Okay. This X bar. Okay. Initially look like this. Right. If I have 3 outcome. Okay. And later you have this. When n increase. Okay. Right. This is maybe this is X bar 1, right? And this is X bar 2 sample, right? And later you will see 3 will like this. You will try to have a sample of 3. Okay. And then you can easily see at the end of the day, in general, look like this guy. It's a bell. Okay. So what he said is, and of course, law of large numbers said this bell would squeeze and become a straight line. Okay, that is what the law of large number and the variance said. But before you squeeze into one thing, it's still a bell. Okay, so that is a sample mean. Basically, sample mean looks like a bell. Okay, that is central limit theorem means. Okay, And if you want a precise statement, okay, I mean, this is looks like when I try to show you this is the graph I actually draw there. But what it means is the following. The sample mean follow a bell curve with mean mu, sigma square n. Okay, so that is very important because this underlines what we do for the rest of semester. Okay, because that is very important. Central limit theorem. Okay. Do note the very amazing part is we do not need to know how the underlying population looks like. It can be anything. Okay, so what I try to say is the following. Why so powerful? Because central limit theorem said the following. Even the x looks like this. Okay, whatever you think. If I try to pick some number from here, okay, pick some number from here, pick a number from here, right? And I have a sample mean that will look like a bar if n is big enough. If n is big. Okay, is original, the population can be any shape, can be any shape you can imagine. There's no restriction. Whatever distribution you can imagine. Okay, if you try to grab data from a random sample, okay, so you calculate the sample mean, okay, no matter what underlying looks like crazy, doesn't really matter. The sample mean is still a bell. It's an amazing result. Okay, and you can look at statistics. Basically, people spend life to prove different version how this is true. Okay, and this all the researcher, many researchers do this. It's basically try to prove this whole for every kind of scenario. This is also true. Okay. So that's why bell curve, as I said, is very important because we care about sample mean, right? And turn out that the sample mean is follow normal if the sample size is big enough. Of course, the sample size is not big enough, then can be any weird shape. But when it's big enough, then it's always normal. So regardless of origin looks like. Okay. So of course you can do standardization minus mu over this guy over its own variance. So do note that because of sample mean, you have to take square root because square root of this guy. Right? You standardize by dividing by standard deviation. Right? So that is something need to be a little bit more careful. Okay. And probably you ask, okay, I said the sample size large enough, but what do you mean by large enough in your work? Very luckily, large enough is not that large. Turn out to be 35, then you can do it. Okay, so not something like you are worrying about 1,000, 100. No. Just 30 something, then it's fine. You can do that. Okay, it's a way amazing, right? Because it's not something like I'm asking 100, 1,000, 1 billion, right? Not, right? The center field actually already apply when more than 50. That's why we can do what we want. Okay, that is why we learn bell curve, right? 30 something for business application is nothing, right? If you can't get more than 30, then probably your business should get out of business, right? Even you want to do something, you cannot get 35. So it's not a concern for us. You'll be concerned for when you are doing medical experiment, right? Each patient you do medical tests can be very expensive, but for most of business study, it's not a concern, right? For medical study can be a concern because you look at their study, maybe 10, 30, 40 is very normal. Usually you get 50 is already very luxury, right? Because you have to fund the patient to get the drugs and so on and so forth. That's very expensive. But for business, yeah, no problem. Definitely no problem. Okay. I haven't seen anything that actually can't work. Okay. So now here we have some idea. Okay. let's put it in practice. Although we didn't actually use it for the next week, okay? But this idea we will be using very important tools. This thing will come back again, is the following. So consider the case that we know for sure a population have mean 5, variance 64. So which means mu is 5 and sigma square is 64. Okay. So it implies sigma is 8. Okay. I hope that's clear. Now we have sample size of 100. So n is 100. Okay. So the question is probability that the sample mean is no more than 4. Okay. So you ask why we do that, it will be clear later. For example, we want to do hypothesis testing. Here we have the first line, we say the population is 5, is we know it, right? How can we know this? We don't know, right? But suppose we know this, how we calculate. But that we can reverse the question, right? We want to look at if this is true, how likely we got this. If this is not true, if this is very small, then we question this guy. Okay, that is actually we call hypothesis testing. We do it 2 weeks later. Okay, let me repeat the statement here is we assume the population follows certain thing. We derive probability. Okay, that's what we do here now. But you can imagine the real world, we never know the population, right? So we want to go backward, right? Assuming what the client tell you, what people told is true. We calculate the probability to observe what we observe. If very small, then you would say the assumption we try to make is wrong. But we will talk about this very carefully later. Okay? Okay, but that is the idea. Okay? So how do we do that? Okay? So this is the thing is being asked, right? But you do remember we will invoke central limit theorem. Central limit theorem was this guy, n is 100, it applies. That means has a normal distribution, right? With mean mu, which is 100, so it is 5, right? And variance is 64 over n is 100, right? So you can put there, look at the table, then we are done. Is that clear? And because remember how to do it is x bar minus mu over this over n, right? Or that is x bar minus 5 over 8 over root 100, right? It's normal CO1. Okay. And all right. So you can do the same operation on the both side equation. Right. Maybe I just do once here. Probably you would see how I get this. How I get here to here. Okay. That's very simple. This inequality, right? So let me do this. Probability. X bar minus 4, right? So you'll be same if we subtract 5 from the both sides, right? This will not change inequality. I hope that's clear, right? And if I divide both sides by 8 over root 100, that will keep the same, right? Because I don't do anything, right? I didn't do anything. The same inequality. Okay. And this is just Z, right? So that's continue to here. Is that clear how I get from that? You subtract the same thing from both sides of inequality and divide the same thing from both sides because they're positive. Right? You learn inequality, right? In the high school. You subtract and add the same thing on both sides, inequality remain the same, right? And then you divide the same number on both sides, inequality remain the same, right? So that's why, but the left-hand side is a standard normal, right? cos Z. So you can just do that. Look at the table, then we're done. Okay. And the Z less than negative 1.25, right? Is that clear? Of course, this is just if you're being Excel, you don't have to go all the way, right? Basically, we just do the norm, this, right? 4 and 5. I think you put the standard deviation. So you put 8 over 10 and then true. Okay, so this gives you the answer directly, right? Of course, you don't want to do this Z table, right? You can just directly input, but at the background, they do that, right? Basically normalize, right? It's just this and dy and then do the same, right? Is that clear? Is that okay? Norm this, I mean, you learned it in last class, right? Is that okay? Don't worry this example because you'll be doing this all the time. In the upcoming semester, we will doing all this quite frequent. Okay. Is that okay? Yeah, it's okay. So look like this, okay? Look at the right-hand side. I'm not going to this one, but I just briefly tell you what is going on because only 1 minute left. So what we have is any number, okay? But what happened is you have CO1, okay? When CO1, the mean is just proportion. How many of them? Okay. And the proportion is called population pi. And this become a Benoni trial because the guy is 1 or 0 with probability pi. Okay. And that's why things become much more easy. But later you will see you don't need central limit theorem. Okay. But you can still apply central limit theorem. That's fine. Okay. They call it binomial. But I guess we should talk about this next week. Just to remind you, next week, I think next Wednesday class, we'll be going through Python. Okay, we do some Python. So make sure that we will do a Google Colab. So as long as you have a iPad or the laptop should be fine. Okay. If not, then if you don't want to bring, you can attend the B.B.A lab section. Also fine. Okay. So next Wednesday, either you attend a class or you go to the lab section. If you don't want to bring anything, but as long as iPad, then you're fine. Okay. We'll use the Google Colab to do the online programming Python. So we'll teach you the basics. Okay. So it's optional. If you don't want to attend the Wednesday one, it's fine. Optional means not really optional. It just means that they are not in the exam or in the assignment. Okay. That's optional means. Okay. Okay. I'll see you next week.